Hey Earth Science fans, remember how last lesson we talked about red supergiants, or when really large stars get to the end of their life, how they grow huge and they turn red? Well, there's a red supergiant called UY Scuti, and it's 1,700 times the size of our sun. This is the largest red supergiant or largest star that we've discovered so far in the universe. And here it is to scale. And by the way, about that name, from what I understand, it's in the Scutum constellation or group of stars, so that's why it's called Scuti, and UY, those letters refer to its location within that constellation. Here's another example of how massive the star is, and a couple other famous stars that are out there. So this is Aldebaran. This one right here is 44 times the size of our sun. Rigel, a little bit bigger. Antares, much bigger. Betelgeuse, a really famous star, that's 1,000 times the size of our sun. So Betelgeuse is this huge, and here it is compared to some of these other supergiants. And this is UY Scuti, 1,700 times the size of our sun. What a massive, massive supergiant. Just a couple interesting things about stars in general. There's blue supergiants as well as red supergiants. And a lot of solar systems out there have two stars. Those are called binary star systems. Ours just happens to have one. We have one sun, but some scientists think that it might be more common for solar systems to have two stars. And sometimes these binary systems, the stars are rotating or orbiting a point so closely that they're actually merged together with their gravitational pull. So they're called contact stars. They're always touching and orbiting each other, spinning around. And last lesson we talked about white dwarfs, or like really old stars that slowly burn off the rest of their energy. Well, scientists believe there's actually a stage right after that when all of the energy is gone and just the solid core of the star remains, which in some cases would be carbon, a crystallized solid carbon, which means that right after a white dwarf, there could be a planet-sized diamond floating out there, and scientists believe that they're just hard to see, but based on the composition of the core of stars and carbon and how they would crystallize when they were compressed under so much pressure, we believe there's planet-sized diamonds out there, or really dead stars that turned into diamonds when they died. So as you guys are keeping up with your thinking rights, definitely going to want to check this one out. This video here is another size comparison between our sun and some of the massive supergiants out there in our galaxy and even beyond in other parts of the universe. So definitely check that out and answer the thinking right questions below. So this right here is a really famous graph in science. This is an HR diagram, or a Hertzsprung-Russell diagram, named after the scientists who created it. And it's famous because it just organizes information about stars in a visually pleasing, kind of beautiful way that helps us understand it. Now, there's a lot of information on here. So first, let's take a moment and see all the pieces of information about stars that this graph shows. For example, I'll start us off with one. This graph shows the color of the stars. What else does it show besides color? So the next one I saw was temperature, because it's right there by color. So it also shows the temperature of these stars, and notice where the hotter temperatures are. I'm seeing, as I'm looking and trying to decode what's in this graph, that the higher numbers are on the left and the lower numbers are on the right, which is kind of odd. I feel like most graphs have the low numbers on the left, but if that's how they have it, that's okay. So just knowing that, okay, the hotter temperatures are on the left and the lower temperatures on the right. And I'm also immediately making a connection, I'll color this blue, that the blue stars are going to be hotter than the red. I'm just noticing that, okay, so the red's on the lower side and the blue's on the higher side. Next, I'm going to look over here. I see luminosity, and just a little more information to bring in. Luminosity means the brightness, so how bright these stars are. And it's relative to the sun, which means that luminosity is a comparison of brightness to the sun. They named the sun a luminosity of 1, and it's right there exactly on the 1 line. So if a star has a luminosity of 10, and Sirius is a little more than that, but it would be 10 times brighter than the sun. These are 100 times brighter than the sun. These are 10,000 times brighter than the sun. So we also have a log scale, which means that they're going up exponentially by 10. So they're getting really, really bright as we go up here towards these stars. This HR diagram also shows the stage of a star. We have an early stage here. We have our intermediate stage up here and here. And we have our late stage. And the stage connects to what we learned in our last lesson about the life cycle of a star. So connecting and just a reminder of what that was. Stars begin their life and most of their life goes in the main sequence, like their childhood through their adulthood of their life. And then as they get older, they grow in size when they're starting to run out of energy. And if they're an average-sized main sequence star, they go and they become giants. And if they're a large main sequence star, they become supergiants. So after the main sequence, they move to the supergiant or the giant section. Finally, when they have almost all run out of energy, gravity takes over, they shed their outer layer. If it's a supergiant, it explodes, and then they move to white dwarfs. So this is where they live out most of the rest of their life as they slowly burn off their energy. So another thing this graph shows us is the stage in the life cycle of stars. And this is kind of implied by other parts of the graph, but they also make it very clear the size of the stars. So we're going to have massive stars on the top and smaller stars on the bottom. So size is increasing as we go up this HR diagram. I'm going to go back to life stage just for a second to make something clear that I may not have before. All of these are main sequence stars. That whole diagonal section across are main sequence. And then again, as if it's like an average main sequence star, it'll go that way. So that's the first path. If it's a large main sequence star, it'll go that way. So that would be the second path. So stars could have two different paths depending on their size. And then eventually they're going to make their way down here. Unless these supergiants would go off and become black holes. So there might be another path that's not on here because they don't consider black hole stars really, whereas a white dwarf is like a dead star, so it is on here. So again, they start out here, main sequence, this whole area. If they're down here, average stars, they're going to become giants. If they're up here, they're going to become supergiants. And then they either explode and become black holes if they are supergiants, or if they're giants, they're going to come down here and become white dwarfs. So you're going to be using this HR diagram for the work today, and I don't want to give too much more away about it. And aside from this just being a cool graph for scientists and a famous one in the history of science, as I'm reading, it just reminds me of all the other solar systems out there and all the other stars and how some of them are huge, and wondering what type of planets orbit those stars, and could there be aliens there. So it is just a graph in science class, but it does open me up to the possibilities of other solar systems and other worlds and possibly other life out there. So much more than just a simple graph. That's it for me. Hope you guys be good out there, stay safe, and I'll talk to you next time.